Hey, welcome everyone. My name's Anton Call. This is Calculus 2, Math 142. Online learning is obviously more difficult than face-to-face. I wish we could be face-to-face, but here's where it's at. So let's get started. I think what we're going to talk about today should be review for all of you, I think. The topic is what I usually call U substitution. So it's the substitution rule, U sub U substitution. And it goes like this. So if you have an integral of the following form, so it's f of g of x, we've got composition of functions followed by g prime of x dx. Now what we do, this is the u part of the substitution, so if we let u equal g of x, then computing du, it becomes g prime of x dx. Okay? So now when we substitute, what we get, f of g of x becomes f of u, and then the g prime of x dx becomes du. Right? So this formula right here is the substitution rule, or what we refer to as u substitution. And the idea is, hopefully it takes a complicated integral and replaces it with something much more simple, right? Hopefully, preferably, something for which we have a formula for, right? So there's the general idea. So let's work on some examples here. The first example, let's do integral, I'm going to start with an easy one, integral 2x times x squared plus 1 raised to the third power. Right? So 2x, x squared plus 1 cubed dx. Now, what I'm going to do is I'm going to choose u equal to x squared plus 1. Now, why do I make that choice? Well, think about how substitution works. You choose some portion, you let that equal u, and then when you take the derivative, right, the du part should resemble some other portion of the integrand. That's the idea. So when we compute du, what we get is a 2x dx, and though it's split apart, what we have is that combined with that, that's our du. And so when we substitute, what we get is u cubed du. This part combined with that part, that's my du. Well, all right, so this worked out nicely. What it did, it took a complicated looking integral, replaced it with something for which I know the antiderivative of, so this is u to the fourth over 4 plus c. Now, this is not the final answer. Our original integrand had variable x. We need our answer to have variable x, and so we substitute back. This is equal to x squared plus 1 to the fourth divided by 4 plus c. So there's substitution in action. The idea is to choose some portion of the integrand, call it u, take the derivative, du should resemble some other portion of the integrand, and then when you put it together, what you want to have is an integral that involves just the variable u. So let's do some more examples. Next one, let's look at integral of x over 3x squared plus 2 raised to the fourth dx. So in this case, the right choice is to let u equal 3x squared plus 2, du equals 6x dx. Now, I mean, when you're doing substitution, you just have to choose some portion, call that u. Sometimes you make the wrong choice, right? But as you practice this, you'll start to learn, oh, you're looking for something whose derivative resembles some other portion. Well, if I choose 3x squared plus 2 to equal u, its derivative is a constant multiple of some other portion of the integrand. Now, what I often like to do is to solve for dx, so dx equals du over 6x. And now let's go back and substitute. What we have is an x over u to the fourth, and then notice dx becomes du over 6x. And now, if I cancel the x's, what we're left with is a 1/6 integral 1 over u to the 4th du. Notice I had this 6 in the denominator, which I pulled out and wrote as 1/6 in front of the integrand. To compute this integral, you might want to rewrite this as integral u to the -4 du. And then when we compute the antiderivative, we get 1/6 times, this will be a u to the -3 over -3 plus c. I don't need to put the plus c out there, do I? Put it there. Okay, so let's clean things up now. This becomes, well, it becomes a negative 1/18, 1 over 18, and then the u to the -3 I can write in the denominator as a u cubed. So we get a negative 1 over 18 u cubed plus c, and then final answer, when we substitute back, what we get is negative 1 over 18, and then u was a 3x squared plus 2, like that. Okay, next example. So here's the idea. The principle behind substitution, what you're trying to do is make a substitution, choose some portion, call it equal to u, so that when you're done, when you've done the substitution, you have some integral for which you know the formula for. So this next example, let's look at the sine of 3x dx. Now, I know the formula for, and you learned this back in Calc 1, the antiderivative of sine of x, right? Everybody knows. Now we've got sine of 3x, and here's a place where substitution can help us out. If we let u equal 3x, then du equals 3 dx. And if you solve for dx, you get dx equals du over 3. And so now when we substitute, this becomes integral sine of u, and then we have a du over 3. That's going to be a 1/3 integral sine of u du. So by letting u equal 3x and applying the substitution, once we clean things up, we now have sine of u. I know the antiderivative of that, so this becomes a 1/3, and then we get a negative cosine of u plus c. And when we clean things up and substitute back, what we get is a negative 1/3 cosine of 3x plus c. We can generalize this. I mean, we did the example here where we've got a 3x. We could generalize this though. So let's say more generally. If we want to do the antiderivative of sine of ax dx, where a is any non-zero constant, by applying the same principle, letting u equal ax, and doing the same computation, what we'll find is that we get negative 1 over a cosine of ax plus c. Also, we could go through the same process, so we might as well get this one over with also. Cosine of ax dx. If you let u equal ax, go through the substitution process, what you'll find is that you get 1 over a times sine of ax plus c. All of this here, we need a not equal to 0. These integrals come up enough, that should be a 1 over a, not a 1/9. These integrals come up enough that it's worth memorizing, right? You don't want to have to do substitution every time. We're going to be computing the integral of sine of ax and cosine of ax all the time in this class, right? So these are two that are worth memorizing. So let's put these in a box. Right? You're going to need to know those facts. Okay, so let's do some more examples now of substitution. So here we've got integral x squared times secant squared of x cubed dx. So remember, you want to choose some portion of the integrand whose derivative is a multiple, if possible, it's a multiple of some other. If we choose u equal to x cubed, then its derivative will be a 3x squared. So that seems like a good choice for u. U equals x cubed, du equals 3x squared dx, which means dx equals du over 3x squared. And now when we substitute, what we'll get is integral secant squared of u. Well, let me take that a little slower here. Let me do the cancellation. So this will be an x squared secant squared of u, and then dx is du over 3x squared. So now notice the x squareds cancel, and we're left with a 1/3 integral secant squared of u du. And this is good. I know the formula for the antiderivative of secant squared. All right, so we get a 1/3 tangent of u plus c. And then when we substitute back, we get a 1/3 tangent x cubed plus c. Substitution, when it comes to integration techniques, is by far the most common, I shouldn't say most popular, but the most useful. Right? So in this class, we're going to learn a bunch of integration techniques. Substitution is the one that comes up the most. You could say it's the most important. Now, I'm going to do a couple more examples here. So this next one, x times square root of x minus 1 dx. This is definitely one that I don't know the formula for, right? So substitution is going to be the way to go. So in this case, I need to make a choice. I'm going to let u equal x minus 1. And then du, let me take the derivative, is just dx. So now we substitute, and so this will be an x times the square root of u times du. And when you look at it at first glance, it looks like substitution failed. When you have done your substitution, you need to have an integrand that involves entirely only the variable u. Right now we've got a mixture of variables. Well, that's okay, because what I'm going to do is I'm going to look at my substitution equation. I've got this lingering x here. What can I do with it? Well, if I solve, what we find is that x is equal to u plus 1. And now I can take that and substitute, and so what we get is a u plus 1 times square root of u du. Okay, so now we have an integral that's entirely in terms of the variable u, and it may not look any better than the original, but it actually is. If I do the distributive property, what we get is a u to the 3/2 plus u to the 1/2 du. And then, let's take the antiderivative here. This is a u to the 5/2 over 5/2 plus u to the 3/2 over 3/2 plus c. And final step, when we substitute back, this will be x minus 1 to the 5/2 over 5/2 plus x minus 1 to the 3/2 over 3/2 plus c. You could simplify this slightly if you like, but I'm fine. There's the answer. I'm fine with that. So here's the idea. When you do substitution, if you end up with something that has a mixture of variables, both x and u, go back to the original substitution equation and see if you can use that to eliminate any lingering x's that remain in the integrand. So let's try another example that's kind of like this one. So this will be integral of x to the 5th times square root 1 plus x squared dx. So here we go. My choice for u is going to be a 1 plus x squared, which means that du is 2x dx, which means that dx equals du over 2x. Okay, so now we substitute, and so we'll have an x to the 5th, and then we'll have a square root of u, and then for my dx, I'll have a du over 2x. Now, I can write this as a 1/2 integral. Now, x's are going to cancel. I'm going to have x to the 5th in the numerator. I've got an x in the denominator. That leaves me with an x to the 4th. And then I have a square root of u du. So I've got a mixture of x's, x's and u's. I need to go back to my substitution equation. Well, x squared is equal to u minus 1. And so if I square that, I get x to the 4th is u minus 1 squared. And so now I can replace that x to the 4th with a u minus 1 quantity squared times square root of u du. Now, this is something that we can compute the integral of. If we first multiply things out, this is a u squared minus 2u plus 1 times square root of u du. That's going to be a 1/2. Now I'm going to distribute, so this will be a 1/2 u to the 5/2 minus 2u to the 3/2 plus u to the 1/2 du. So all I did was multiply this portion out right here. And then we get a 1/2 times, this will be u to the 7/2 over 7/2 minus 2u to the 5/2 over 5/2 plus u to the 3/2 over 3/2 plus c. And now final step, I need to get everything back in terms of x. So I'm going to take my u and substitute it in. So this will be a 1 plus x squared to the 7/2 over 7/2 minus 2, 1 plus x to the 1 plus x squared to the 5/2 over 5/2 plus 1 plus x squared to the 3/2 over 3/2 plus c. So the answer's not beautiful, and you could simplify this more if you want, but I'm happy with the answer just as it is. You don't have to simplify things any farther than that if you don't want to. Okay, now what we've looked at so far, we've been doing substitution with antiderivatives, but you can also do substitution with definite integrals. So let's say here now u sub and definite integrals. So the formula is going to look similar. We start off with our integrand exactly the same. Right, so we're integrating something of the form f of g of x times g prime of x dx. But instead of being an antiderivative, we want a definite integral now, so I have limits of integration. We do exactly the same thing. We let u equal g of x. Du is g prime of x dx. When we substitute, we're going to have as an integrand f of u du just as before, but now our original limits, a and b, correspond to the variable x. So we have now switched to the variable u. We need to know what is u in those cases. So When x equals a, if I go to my substitution equation, u is equal to g of a. When x equals b, u is equal to g of b. So that's the formula for substitution. When you're doing a definite integral, you need to change the limits of integration to g of a and g of b. Okay, so let's try a couple of examples there. So first one, let's look at the integral from 0 to pi over 3. Cosine cubed x times sine of x dx. In this case, I'm going to let u equal cosine x, and then du will be a minus sine x dx. So when we substitute, let's do the substitution part first. So let's see, I'm going to get a, that minus sign is going to be, I want to put that out front, so it'll be a negative u cubed du. Notice right here, that's du except for the minus sign, and I just put it out front. Now the limits of integration, I take my lower limit, plug it in for x. When when x equals 0, u equals cosine of 0, which is 1. When x equals pi over 3, u equals cosine of pi over 3, which is 1/2. If I can avoid a minus sign, I will. So remember, if you flip the limits, you get rid of the minus sign. This will be an integral 1/2 to 1 u cubed du. That's going to be a u to the 4th over 4, and now we evaluate from 1/2, from 1 to 1/2, or 1/2 to 1, I should say. So that's equal to a 1/4 minus, this will be a, 1/16 times 4, yeah, 1/64. And so I guess we get 15 over 64. Now, one thing to notice, many of you may have learned to do substitution slightly differently where you don't change the limits. And it's fine, it works. You can do a process where you don't change the limits, you compute an antiderivative and then plug the original limits back in. But we're going to get to a place in this class where we're going to be doing multiple substitutions using a couple of different substitution techniques. It is in your best interest to learn how to change the limits now. So the idea is, old limits, 0 and pi over 3, got plugged into the substitution equation to give us the new limits. And then as we carry it through, notice I do not do any substitution anymore. I plug the new limits into the u function. I don't need to do any back substitution. That's the benefit of changing the limits. There's no back substitution involved. So let's do another example. Okay, so this is integral from, I didn't put any limits on my, I'm going to put some limits here. Okay, so let's just go 0 to 1. X over 3x squared plus 2 raised to the 3rd power dx. This one's similar to one that we did a little while ago. We let u equal 3x squared plus 2, du equals 6x dx, dx equals du over 6x, right? So there's the substitution setup. Okay, so we're going to pick a 1/6. There's a 6 in the denominator. I'm going to put that out in front. This x is going to cancel with that x when we substitute. So our integrand will be a 1 over u cubed du. Now, the limits, when x equals 0, u equals 2. When x equals 1, u equals 5. Right, so there's the new limits. Now we compute the antiderivative as usual. This will give us a negative 1 over u squared, and we evaluate from 2 to 5. That's going to be a 1/6 times negative 1 over 25 plus 1 over 4. We can simplify this one, so this becomes a 1/6 times negative 4 over 100. I'm just getting a common denominator, plus 25 over 100. And so this will become positive. It'll be 21 over 600. And if we factor out a 3, that's going to be a 7 over 200. Okay, so there's how substitution works with definite integrals. Okay, one last topic, and this is, we'll call this definite integrals and symmetry. Now I need a definition first. So a function f of x is even if f of minus x is equal to f of x. And a second part of this definition, it's odd if f of minus x is equal to minus f of x. So really two definitions here. We've got even functions, we've got odd functions. And here's the picture. It's even if it's symmetric about the y-axis. So here's an example of the graph of an even function, right? And so what are we saying here? If I choose a point minus x, if I choose x here, and then I look at minus x on the reverse side, go up, hit the graph, go up and hit the graph, right? They're at the same height. F of x and f of minus x are the same. Right? So a function that's symmetric about the y-axis, that's one that we call an even function. Now an odd function that was not a good job. Let's try that again. So an odd function, and I'm not the greatest artist in the world, but here's x, and here's minus x. So if you go up and hit the graph with x, you go down and hit the graph with minus x, and you compare, this distance and this distance are the same. So what we have, here's f of x, and here is f of minus x, and they're negatives of each other. So that's the idea behind an odd function. Now, the symmetry of a graph can sometimes simplify the computation of a definite integral. So here's the result, or theorem. If f of x is even, then the integral from minus a to positive a of f of x is equal to 2 times the integral minus a, 2 times the integral from 0 to a of f of x. So the point is, if you integrate, I know I call them x and minus x here. If I go from minus a to positive a, this area right here is equal to this area right here. So if you want to compute, oops, I stepped out of the shot there. If you want to compute the definite integral from the left-hand side to the right-hand side, you can do that by going from the origin to the right-hand side and doubling the result. And this will often simplify the computation. So in class later on, I'll say, hey, should we use some symmetry to compute this? And it makes the arithmetic a little bit easier. Now, so there's the first part. The second part of the theorem, if f of x is odd, then when we compute the integral from minus a to positive a, f of x dx, notice that the area under the graph here matches the area right there, but one's above the x-axis, one's below the x-axis, so they'll have the same area. One's negative, one's positive, they cancel out, and so what we get is 0. So let's just do a quick example. Well, actually, we'll do two examples, one of an even and one of an odd. Cosine is an example of an even function, right? If you look at the graph of cosine, I mean, it goes up and down and up and down. But so the right-hand side is the mirror image of the left-hand side. It's symmetric about the y-axis. And so if I compute integral from minus pi over 4 to pi over 4 of cosine of x dx, because it's an even function, it's equal to 2 times the integral from 0 to pi over 4 of cosine x dx. And what we'll see, I'm not going to compute this out, you can do this on your own, but it does make the arithmetic a little bit easier because now when you plug in a 0, it eliminates some subtraction that you have to do in the final computation. And then the next example, integral from minus pi over 6 to pi over 6 of tangent of x dx. Tangent is an odd function. Think about the graph, right? It's got these asymptotes, and then tangent has a graph that looks like that. Because tangent is odd, that integral is 0, and that's good because we don't even know how to integrate the tangent at this point right now. We will learn the formula for the tangent, but at this point, we have not learned the integral formula for tangent of x. Okay, so that's a good place to stop for today, and we'll see you next time.